Right, so we're going to continue talking about circular motion. I'm going to finish this part up. Today, I'm going to give you one more example with uniform circular motion, and I'm going to briefly cover gravitation and gravity and how this relates. I'm going to go through that pretty quickly because it is a rather complex topic, but I want you to see it and how it relates here. So the problem that I want to start working on for you guys today is this. Let's say that we have an inclined plane. There's a car on the inclined plane, and it's kind of going around. This is a racetrack, right? So you're going to be kind of at some angle, theta, on the racetrack. Now we kind of know from our discussion of centripetal force, centripetal acceleration, that we're going to get some sort of force going on here because the car is going in a circle. And we can kind of tell from just our intuition and our observation that at some point, this car is going to be going so fast that it's not going to stay on the track. It's going to go fly off. So what I'd like to know is, what is that limit? What's the speed limit? What's the velocity at which I can go around this track with a given bang and not fly off? Seems pretty useful to know. So we're going to apply a couple of techniques to solve this problem. The first thing that we need to look at before we start making things complex, remember, kind of look at the simple case. So the first thing I'm going to do is assume that my car sits on some flat surface, not moving, just stationary. Now, we already know from our previous work that we can pretty easily figure out the forces that are involved here. Since the vehicle is in equilibrium, meaning all forces acting under zero, Newton's second law says sum of all forces has to be the mass times the acceleration. If there is no acceleration in any direction, sum of those forces has to be zero. So we know this thing is stationary. So the only forces that we really know about at this point are the gravitational force and the normal force. So remember, gravitational force is just mg, the mass of the vehicle, times the acceleration due to gravity. And we know that the normal force has got to be the opposite of the force due to gravity, which is just going to be our negative mg. Let's say, just to keep things kind of in a frame of reference we understand, let's say that down is our negative direction. So that makes the force due to gravity a negative mg. The opposite of that would be positive mg. Gravity acts downwards, thus we have a negative acceleration vector. Now let's say that we come along and we apply some force, we'll call that the applied force, F sub A, on the car. As soon as we apply a force, there must be an equal and opposite force. And we're going to say that's the force of friction. So remember, the force due to friction is the kind of measurement of how hard it is to move this thing. It is a function of the weight, and it is a function of something called the coefficient of friction. And if you remember, that frictional force is just mu, coefficient of friction, times the normal force. In this case, we know what the normal force is. So this ends up being mu mg. Notice that I have not put any kind of value to this, right? I've not put any kind of numbers in here. All I'm doing is figuring out what forces exist. So for a car arbitrarily going around the track, if there's some sideways motion, then that's going to be countered by some force due to friction, which is a function of coefficient of friction and the normal force. Cool. Well, we know that the car is kind of going around the circle. And it's going around the circle at some velocity v. So if we were to look at this from an overhead perspective, we got some angular there and some velocity. So we are trying to find out ultimately what this velocity can be. Well, since we're moving in a circle, we know that we're going to have a centrifugal force. Centrifugal acceleration, right? We know that's got to happen because there's rotational motion. Well, if you think about this a little bit, remember that we can find that centrifugal force with mv squared over r, where r is the radius of the circle. Now we need to do a little bit of thinking. So we know that in order for this car to stay on the track, that this force due to friction, right? So think about this, it's kind of acting towards the middle of the track. That means because we're moving in a circle, we have some centrifugal force. For the car to stay on the track and not move up or down, the value of the centrifugal force and the value of the frictional force have to be equal. If they're not, then you get oscillation towards the center or away from the center. This is exactly what we don't want to happen. So the point at which the thing is going to start moving in one direction or the other is the point where those forces are exactly equal. And if you apply just a little bit of force one way or the other, it's going to move. So we can say, for our case, we want to find the point where the force due to friction is equal to the centrifugal force. Well, let's do a quick example. Let's say that our circular track has a radius of 400 meters. And let's say that our coefficient of friction, mu, is 0.7. Remember, this is a unitless value, the coefficient of friction. We can do some things pretty quickly here. We can find that the frictional force then must be mu mg, right? We know the centrifugal force is mv squared over r. Well, if we set these two equal to each other, what we're going to find, since centrifugal force is mv squared over r, this backwards, but it doesn't really matter. The frictional force is mu mg. We can cancel a bunch of stuff, right? One of the more interesting things that cancels is the mass. So that means that ultimately these forces do not depend necessarily directly on the mass of the vehicle as far as balancing the centrifugal force. Now, why is that? That's because the centrifugal force, yes, is a function of mass, but so is the frictional force, but it's a function of the same mass, and they're on either side of the equation. So the mass in this case is effectively going to cancel. So what we end up with, just doing a little algebra, is we get a value for v squared equals mu gr. Plug in the numbers that we know, right? So v equals square root 0.7 for our mu that gave you. Our acceleration due to gravity are 9.81 meters per second squared. And our r of 400 meters. Again, I'm dropping units for expediency here, but remember, all of this has to be in SI units. If you don't convert to meters and seconds and meters per second squared, you're going to get screwed. So, assuming we've done all that right, that works out to be 52 meters per second is our velocity. If you do a little bit of conversion work on that, that gives us a speed of about 117 miles an hour. So let's go back and review what that means. That means if this car goes around the turn and it's a flat turn, and our radius is 400 meters, so that's a pretty wide turn, and the coefficient of friction is 0.7. I don't know what the equivalent condition of that would be. Let's say it's dry pavement and rubber tires, so 0.7. The fastest you could make that turn without sliding off the road is going to be 52 meters per second, or 117 miles an hour. So let's do some sanity check on that. I think we all have a pretty good handle on what 117 miles an hour sort of looks like. And 400 meters, if you want to convert that to feet, it's a little more than 3 times that in feet. So a little more than 1,200 feet, so let's say 1,500. So you're looking at about a quarter mile, right? So a quarter mile is the size of your standard running track at a high school or something. So, but remember, those tracks are oval. So if we kind of compress and distort that into a circle, that's a pretty big circle. And we can go around that 117 miles an hour. Now, remember, that is assuming the mass is constant. It's assuming the coefficient of friction is constant, so we're not hitting any greasy spots or anything. And that's exactly the point where these two are going to equal. So probably not a smart idea to go out and actually test that, because there's going to be a lot of other factors there. But remember, we're doing spherical count vacuum kind of problems. We want to know the absolute maximum speed. Now, what engineers do in these cases, if they're trying to design something like this, what they'll do is they'll find the absolute, in our case, 117 miles an hour, and then they will generally add a safety factor, let's say a 50% safety factor. So basically, they'll post a maximum speed limit sign for this turn and take half of 117. So that's about 60 miles an hour is what they're going to say the absolute maximum you try to navigate that turn is. Now, physics tells me if everything stays constant, I can do it twice that fast, but I don't want to take that chance. Well, that's cool. That's pretty fast. But let's think about the situation where this is no longer Interstate 40. Even though people think Interstate 40 is a NASCAR track, sometimes it is not. It's not built for you to be making these very, very fast, tight turns. So they tend to be flat. But let's take the case of the NASCAR track. Talladega, for example. It's got a really steep bank angle. I think it's on the order of 40 degrees or something, pretty large. So here's a car, same kind of setup. Now we're going to do something a little different. We're going to introduce theta and label a couple of things here. We know that we have a force due to gravity here, and we know that we have a normal force. Notice we're going to have an angle in there. So that should be a clue right now that we're going to need some trig. But remember, when we do inclined plane problems, that's all this is. Pushing a box up a hill, right? Nothing new. Remember, we want to align our axes with the direction of motion. The motion that we're interested in is sliding up and down this track. So we know that we're going to have some frictional force here. Right? Well, what we're going to need to do is find some components, right? Because we can't just use the force due to gravity to find our normal force, which is really going to be important to us, right? So we got to get some vectors. So this is going to be our force due to gravity. And let's call it the y, or let's call it the x direction. Actually, you know what? Instead of calling it x, let's say it's the force due to gravity parallel to the ground. And then that makes this the force due to gravity perpendicular to the ground. All right, we can do that. Remember, I'm a physicist, I'm lazy. I can make whatever coordinate system that I want. So we can now say, if we think back to our inclined plane problems, that our perpendicular force of gravity is just going to be force of gravity times the cosine of the angle. That makes our force of gravity perpendicular or parallel to the road, the FG sine theta. Well, what's the force due to gravity? It's just the mass of the vehicle times the acceleration due to gravity. So this ends up being mg cos theta, and this ends up being mg sine theta. So now we have to apply some physics and some critical thinking. Think about what we're trying to find. We want to know how fast the car can go around the turn before the coefficient of friction term gets so small, or this parallel force gets so large that this thing flies off the track, just like we did before. Nothing is different except we've added in this incline, so we've had to do this. So what we're going to find is that our force due to friction, then, this, actually I should probably write that in the same color. The force due to friction, then, in order to hold the car on the track, has to be greater than or equal to this parallel force, right? equal and opposite, we start log in. Well, that means that parallel force looks like mg sine theta. Cool. But we need to know the coefficient or the frictional force now, right? We need to find that frictional force. We know that the force due to friction, we can calculate it with mu n, where mu is just our coefficient of friction, n is our normal force. Well, we can just look at our free body diagram and figure out pretty quickly that our normal force is going to be dependent on this FG perpendicular. And we know FG perpendicular is just mg cos theta from our previous trig. Well, since we know this has to be true, that the force due to friction has got to be greater than or equal to that parallel force, and that parallel force is mg sine theta, we found out that our friction, our normal force then is our mg cosine theta. Well, that means if we plug in this mu, that our frictional force then becomes mu mg cos theta. And that's got to be greater than or equal to mg sine theta. All I'm doing is making substitutions. No big deal. Look what happens. The masses go away. The acceleration of gravity goes away. Again, talking about a constant contained system. You cannot cancel the thetas, remember, because they're bound up in these sine cosine functions. But what we can do is say that mu has got to be greater than or equal to sine theta over cosine theta. And if we remember our trig identities, that's tan theta, right? Sine over cosine is tangent. So all we have to do is put everything together now. Remember, don't lose sight of what we're looking for. We're looking for that max velocity that we can have. Well, we know that the thing that the max velocity is dependent upon is the centrifugal force, mv squared over r, where r is the radius of the turn. That means that our normal force times the sine of our theta has got to be equal to our centrifugal force, right? So we can say that normal force sine theta equals mv squared over r. Well, that is true. So that means that that force then, just do the algebra, has to be mv squared over r sine theta. Well, we also know that the car cannot fall through the surface, right? So this is the circle. Similarly, if we don't want the car going through the road, which awfully can't be true, right? then Fn has got to be mv squared mg over cos theta. Remember, we're just balancing forces. In order for this to be true, both of these have to happen at once, right? To keep the car stable. So we're going to end up with an equation that looks like mv squared over r sine theta equals mg over cos theta. Little simplification here, and we get something that looks like v squared over gr equals sine over cos theta. Well, here we are again. Remember sine theta over cosine theta. That looks sort of like tangent, right? So a little more algebra. We get tan theta equals v squared over gr. Okay. Well, that's kind of cool. Because look what I've done. I found out that the velocity this car can go around the track is totally dependent on the bank angle and the radius of the turn. Obviously, I can't do anything by gravity. So we can plug some numbers in, right? So what happens if, let's say, that we set up a problem where the radius of the turn is 600 meters. We set up a velocity of 56 meters per second. That's what we had before on the flat track. But let's see what the angle does. So if you plug those numbers in, we know R, we know V, then what we can find out is what theta do we need for this to happen? So we plug some numbers in here, and what we're going to find is that our tan theta, that's our V squared, which is 56 squared over our radius times gravity, so 9.81 times 56. I forgot to write down. I had that in meters per second, but this works out to be about 250 miles an hour. Well, that's interesting because on the flat track, we found that we could only do this at 117 miles an hour. So adding this bank to the track means we can go a whole lot faster. This is why you see racetracks that are built that way. This is also why you see high-speed exit ramps and on-ramps on the highway sometimes will be banked like this, especially if you have to change elevation. It's like that. It's common in Germany on the Autobahn, which is really fun to drive on. So that is probably the most complex thing that I would expect you to be able to reproduce for me on a test, is something like figuring out that maximum bank angle. Not too hard, right? There's a lot of pieces to it, but if you break it down one piece at a time, I'll find it's not all that difficult. There's nothing new here. It's just some of the forces. It helps tremendously if you draw those diagrams. Notice in this one that I ended up really doing two diagrams. So that's my kind of side on view. And then I needed some information about the turn. Because we're in a closed system and Newton's second law tells me that all of the forces must be balanced, then we can just combine the two force calculations and solve for the one missing variable that we have. And the missing variable is going to be dependent on what we're looking for, right? We're going to have a known, we're going to have an unknown. You could see, interestingly enough, from the solution to that one, notice that it did not depend on G. G went away. So that means this will work exactly the same on the moon, or on Mars, or Earth, or Jupiter, or an artificial space station, rotating at some acceleration, right? That's kind of cool. It's really interesting to me to see things like that for the first time, to see how the physics behind this actually works, to understand the numbers. Now, a thing that we were very, very interested in early in the 17th century, we started getting involved and interested in gravity. So there was a guy called Johannes Kepler. Johannes Kepler was an astronomer who was the student of a guy called Tycho Brahe, who was also an astronomer. Interesting enough, Brahe, this is not going to be on the test, I just thought it was cool. Brahe had a silver nose. He had lost most of his nose to, I think, a duel with somebody, and had this prosthetic nose made out of silver. Anyway, Johannes Kepler is his student and really advances the study of gravity. And so Kepler comes up with these three laws of gravitational motion. The first one, he says, is that all orbits are ellipses. There is a proof of this that's more of a geometry and a math proof that I am not going to go through because it's a little complex. But if you work through this proof, what you find is that all orbits are ellipses and a circle is just an ellipse. That's all it is. His second law says that if you take some angle and we look at the area that's covered as this object orbits something else, we'll find that this area here and this area here are the same. It's pretty easy to see that in a circle, but this is also true if the thing is an ellipse and it's really stretched out. So this is Kepler's second law of motion. Kepler's third law of motion says that the square of the period is proportional to the cube of the radius. And that's where this rotational motion stuff comes in. Again, I'm not going to go very deeply into this because I haven't shown you how to calculate periods of things and oscillations. We'll get to that towards the end of the semester. But we do know basically how to solve this. So what we need to do to solve the Kepler problem is think of circular motion. So in the center is the sun. And out here, let's just say this is Earth. And we know some radius. And we know the velocity of the Earth around the sun. Sorry to you flat earthers, this is how it works. The sun does not go around the Earth or over the flat Earth. So the Earth goes around the sun. So we know from our study of circular motion that there must be a centrifugal force. And we know that centrifugal force looks like mv squared over r. Should be consistent. Capital R for the radius, doesn't matter. But now we need to know something else. We know this is a closed system. The Earth is not going flying off out into the void of space. So there's got to be something that's pulling the Earth towards the sun that counters the centrifugal force. Well, that force is gravitational force. Call it big G. You'll see why here in a minute. So this is the gravitational force. There is a big, long, complex derivation to this that I am not going to get into, but I want you to see this. The force due to gravity works out to be this. There's something called the universal gravitational constant. This is a unitless value. Actually, it does have units, but they're very, very strange, and nobody ever uses them. This kind of describes gravitation in general. It is a constant that has to go in here to make this work out, because this force is in newtons, right? Because it's a force. It's got to be in newtons, but the gravitational force is dependent on the mass of the two objects. So we'll call the sun M1 and the Earth M2. So M1 times M2, and then R squared is the square of the radius. This is what's called the inverse square law. So what that means is that gravitation has to get weaker between two objects as they move further and further apart. Or if the objects get very, very large and the radius remains the same, the gravitation is going to increase. We use this all the time in observational astronomy. If we have, for example, a binary system, we're looking at two stars orbiting each other. There are things we can do that are extraordinarily complex. And if you really are that interested, take intro astronomy, or if you're advanced level, take intro to astrophysics with Miles Blanton. And you'll get very deep into the ways that we can tell what the masses of these objects are just through observation. Suffice to say, we can. And we know the force due to gravity. So now what we have to do to solve Kepler's problem is we say, well, those forces have to be balanced, right? Our gravitational force has got to equal our centrifugal force. So which mass do we use? Generally, we use the smaller mass. The reason for that is you will find, if you actually work this with real numbers, that in the case of something like the Sun-Earth system, where the sun is much, much larger than the Earth, that the displacement, the orbit of M1 around M2 is going to have a very, very small radius. So the sun actually does orbit the Earth a little bit. In fact, they both orbit what a common center of mass, and there's a way you can find that. But for this problem, where the sun is much, much bigger than the Earth, that common center of mass is almost exactly at the center of the sun anyway. So we do this. So that tells me that Gm1 M2 over R squared is M2 B squared over R. Well, in this case, the velocity that we're interested in is really this angular velocity. So we need to make a substitution, right? Instead of V, we're going to substitute in our omega. And remember that omega is just VR. So we need to do substitution there. So V ends up being omega over R. That whole thing is squared. Omega has to do with orbital period or time, right? It has to do with time. So it's angle per time. So this looks like some sweep, right? Some distance, delta S. So omega, remember, is delta S over T. Delta S is just our arc length. T is our time, whatever that happens to be. We call that the period of the orbit. Again, we'll get into oscillations late in the semester and we'll talk more about that. If you do a couple more substitutions, what you can do is solve for this, and this will come out that this T squared is proportional to R cubed. That is Kepler's third law of planetary motion. I don't expect you to derive it, but if I were to give you a very, very broad overview and ask you to find the radius of an orbit of some object around some other object, given the masses and given velocities, you can find this, right? You'd be able to, but you have to know the physics, right? You have to know that there's got to be two opposing forces, in this case gravitational, because there is no friction. There's no contact, right? Notice there's no such thing as normal force here, because there's no contact. If there's not a contact force, there can't be normal force. And we have centrifugal force that has to happen. This is exactly the car going around the track problem. All we've done is find the two forces that we need. We set that up pretty easily from a diagram. Find the equations for those individual forces, just keeping everything on the same side of the equal sign until we work down to something that has our unknown variable and a whole bunch of other variables that we know. Very, very simple. It's just algebra. Physics is not about algebra. It is not about calculus. Algebra and calculus are tools that we use to answer questions. This is the question, right? What is this radius? What is the mass of this object? The math is trivial, but we need to understand physics and understand the setup for how to solve these problems. That should be enough for you to get through this latest homework. And in the next lecture, we are going to move into the idea of energy, kinetic and potential energy, and law of conservation of energy, which I'm going to warn you up front is really going to make you angry with me, because we're going to go back and we're going to do the same kind of problems. We're going to do it from a different approach using energy, and we're going to find out the energy approach is way, way easier to do than having to mess with vectors. But it's very, very useful, because once we cover energy, then we can talk about energy transfer. And that means collision, which is really fun because we can look at car crashes, billiard balls, that kind of thing. Collisions mean transfer of energy. Energy can also come in the form of heat. I have a problem that we're going to look at, assuming we have a frozen chicken of some given mass. I want to figure out how hard I have to slap that frozen chicken to cook it in one slap. It seems silly, and it is, but it's a useful little physics exercise to go through to understand what we're doing. Okay, so I think that is enough for today, and I will see you guys in the next lecture.